Hello, my name is Chongwon. In this project, I implemented a Fractal Terrain generator using simplex noise along with a Terrain editing system. When the program starts, it first generates a Terrain using a height map. Each point in the Terrain is assigned a height value based on noise, which creates a natural looking. After generating the Terrain, the program these options include raising Terrain, lowering Terrain, flattening Terrain, and save the Terrain as an OBJ file. The user can select an option and input a location, radius, and amount to modify the after multiple edits. The user can choose to save. This file can be opened in external software to visualize the final Terrain. Overall, the program demonstrates how procedural Terrain can be generated and then modified interactively using a height map. Now I will explain my code in detail. Focus on the Terrain editing system that I implemented. First, I create a scanner object to allow user interaction through the console. This is important because my Terrain editing system is interactive, meaning the user can continuously modify the Terrain instead of generating it only once. Next, I use a Boolean variable called editing and a while loop. This loop ensures that the program keeps learning until the user explicitly chooses to exit. This is a key design decision because it allows multiple edits to be applied sequentially to the same height map instead of restarting the program each time. Inside the loop, I print a menu that shows the available Terrain editing operations. Raise Terrain, lower Terrain, flatten Terrain, save and exit. The user selects an option using this input directly controls which algorithm will be applied to the Terrain. I use a switch statement to map user input to specific functions. Instead of writing separate input logic for each case, I designed a single method called applyEdit. This improves code, modularity, and reusability, since all editing operations share the same input structure. The applyEdit function collects four important parameters. These represent X and Z, the center of the editing area, radius, the size of the affected region, amount, the intensity of the height change. This abstraction separates user input logic from Terrain modification logic, which is a good software design practice. In all Terrain editing functions, I iterate over a square region around the center. This ensures that the algorithm does not go out of bounds, only nearby points are considered. Then I calculate the Euclidean distance from the center. This distance is crucial because it determines how much influence each point receives. In the raise Terrain function, I increase the height using this formula. This formula creates a linear fall-off effect. At the center, the full amount is applied. At the edge, the effect becomes zero. This produces a smooth hill shape rather than a sharp spike. The lower Terrain function is structurally identical but subtract height. This symmetry ensures consistency in the Terrain editing behavior. It creates a smooth diffraction or valley using the same distance-based logic. The flattening process consists of two steps. This computes the average height of all points within the radius. This replaces all height value in the region with the average. The result is a uniform flat surface.